So, and we're ready to rock. All right, so today we're going to be talking about the process control and control charting exercise that we have going on this whole semester. You've been collecting your data. Here at the end of this week, if you have 15 data points, or next week, if you have 15 data points, you can start to create your control chart. So we're going to talk about that today, how you should set up the rest of your table. And then you're actually going to see the results of one of the honors contracts. So last year, I had a student doing an honors contract, and we were trying to negotiate what they would do. And I said, listen, I've prepared this notes and this exercise based upon my experience in industry of control charting, but maybe there's more out there in terms of a standard. Like I don't have a standard that I could cite. And so this morning I uploaded that. I went through his work and I found the standard that he found. And so I put up an ASTM standard on the control charting. So you can use that to kind of come up with some of the language in your control chart quality report. It'll be nice to have like a reference that you can refer to for your data and so on, of how you're building your chart and the things that you're doing in your control charting exercise. And then I've put some of those pages in the vocabulary section in today's lecture. So you don't have that in your notes, but that's okay. You'll have the video and you'll have the actual standard. So whatever you see today, you can go back to the video, you can pull up that standard and you can kind of read it on your own. So I'll kind of guide you through that today. So pretty excited about this. So every process, what we want to do is we want to study the inputs so that we can predict the outputs or know more about the outputs. So what are the inputs in your particular case? If you're in a forensics lab, you sometimes you can't tell your outputs. Your output would be an accurate analysis of like a seized drug or some sort of trace material. And so you really don't know what the right answer is. So you're left with making sure your process is stable. And you can run against standard reference materials, but your process variables are various inputs. It might be the behavior of a balance. It might be if it's a process control variable that's really important, it might be the heat on an oven. We had one of those. We had a process where we had to heat the explosive at 120 degrees for so many hours, okay? And then we'd run a test to see the thermal stability of that explosive. Well, the heat of that oven was a process control variable. If that oven fluctuated and didn't heat up to 120 degrees, then those explosives tended to pass, but it wasn't an accurate test, right? Because it wasn't actually aging the explosive. And we discovered this by talking to the technicians. We said an explosive failed, and he said, oh, we used the wrong oven. Well, the scientists were like, oh, that's a warning sign, right? What do you mean you used the wrong oven? They said, well, if we put them in this oven, it always passes. And we put it in this oven, it doesn't pass sometimes. And so we tested the temperature of that oven, and it wasn't 120 degrees. So they sort of knew there was a process control variable they weren't tracking. Okay. So it's a single measurement result. It indicates the performance of the equipment and the process. So the process control variable is unchanging if the process unchanged. So that's what we mean by it's a variable that we can track the process with. So if the process is stable, this variable will be stable. This means it should not change except for random fluctuations. I mean, there'll be some standard or some fluctuations that are within a range of uncertainty. But if it does change significantly, something non-random happened. And so then it's time to investigate. Okay, so I'll let you finish that. So what we're looking for is two things. We're looking for the range of those random fluctuations, and that's where we get that standard deviation, and that's what this learning or training period is. And then we enter into the control period where we're looking for special causes, things that go out of control. And we're going to set our level at 2 sigma. There's lots of ways you can determine if a process is in control or not, and we're just using a 2 sigma level of control. So we've gone through this pretty much. I think everybody has an approved set of data. This is just, again, a review. We're doing a delta in temperature. We're going to do today minus yesterday. Also, I pointed this out in an earlier lecture, but I want to emphasize it again. Your variables need to be a single letter. we have a problem. I don't like for the relative standard deviation. So DW doesn't like. It's really not the ACS style. RSD, right? See, that's 3 letters for one variable. That looks, if you write that in a paper or something, it looks like R times S times D. It looks like there's 3 variables there. And so, but tradition, people have used RSD as the relative standard deviation, but it's really not the ACS style. It should be something else. I mean, I don't know what, maybe it should be SRD, a single letter with subscripts. So that would be the standard relative deviation. I don't know. So I haven't come up with a good one, because if I come up with one, then I'm going to be an odd person out, and RSD is well known. So if you talk about the RSD of a process, that's the relative standard deviation, but that's really not the ACS style, to have 3 capital letters representing a single variable. Do you see how confusing it would be if you didn't know what that was, and you're looking at an equation and you see RSD and you're like, okay, what's R, what's S, and what's D? So we want our variables to be a single letter. You can use all the subscripts you want, okay? And so once you have 15 days, you should compute the mean and the standard deviation for your data using the average and standard deviation population function in Excel, stdev.p. So what you're monitoring and what it means. Like, let's say you're monitoring the daily change in temperature or pressure or pollen or stock prices, okay? What you want to see is the normal random daily fluctuation in the process. Ideally, your variable won't change by very much. And so there'll be a small standard deviation, and then you'll be able to detect any kind of non-random change. If something is outside of 2 sigma, there's like a 2.5% chance that it'll be outside that bounds. Okay. So when a daily difference is more than 2 sigma, then something significant has happened. We call that a special cause. Okay. So these changes are called common cause. And this something significant, we call this a special cause. It's special. Okay. One of the goals, if you look at our control charting exercise, I list several goals. One is to track a process for 15 weeks. Another is to learn about the behavior of continuously variable data. But one of them is to sort of explore data-driven action versus calendar-driven action. So let's discuss that next. So this idea, this control chart philosophy, is called Kanban. It's a Japanese phrase which means signpost. Okay, so calibration checks are often used in industry, and calibration schedules operate on a push philosophy. So let's say you have in your laboratory operation guide that you should come in every morning and you should calibrate the instrument. It seems reasonable, right? So let's say that takes an hour, and you're going to work an 8-hour shift. You've used up 12.5% of your time every day calibrating. What if the instrument doesn't need to be calibrated? You could get a whole nother hour of work done if you didn't need to calibrate that instrument. But it sounds risky, doesn't it? I'm not going to calibrate the instrument. I'm just going to start putting my samples in and run it on Tuesday when I calibrated it on Monday. That seems crazy, right? But you would have a check sample. You would run a control chart to see if the instrument is still in control. And if it's still in control, keep running. Only start calibrating when it goes out of control. So you put a check sample in at the first part of your set of samples, one in the middle, one in later, and you could see those control samples or check samples throughout the day, every day, and only calibrate when you need it. You're assuming that calibration fixes things. What if it makes them worse? What if Monday's calibration was incredible, dead on, And then Tuesdays you come in and calibrate and it wasn't quite as good. Your hand was shaky or whatever. You've just ruined the really good calibration you had on Monday by making it worse on Tuesday. So constantly fiddling with your process actually increases the variability. One day will be a good calibration, the other day will be a bad one, and you're gonna introduce yourself as a new source of error because you might have a bad day and you've introduced statistical variation. So fiddling with the knobs is a bad idea. And fiddling with them on a calendar basis, like you're going to fiddle with the knobs every morning. Can you see how that's going to introduce uncertainty in the process? And so what you would want to do is use this pull philosophy. We want the instrument to tell us when it needs attention. It's like, oh, I'm going to show up a sign that my check sample is more than 2 sigma off, and it's not likely to do that. That's a special cause. So we're going to stop, we're going to recalibrate, and then we're going to put the rest of the samples back in and go. So this is a calibration schedule, might be every day, every week, regardless of need. It's not based on the data, it's based on the calendar. So that's what we mean by calendar-based data, okay, or calendar-based schedules or push philosophy. It's not based on the data. It can increase cost, and it can miss problems that occur between a scheduled calibration, because the schedule requires no performance tracking. So if you're, let's say you're calibrating on a weekly schedule, and on Wednesday the process goes out of control, but you won't know it because you're not going to calibrate till the next Monday. And so the Wednesday, Thursday, Friday samples are they're off because the instrument changed. Now, most analytical chemistry procedures would have check samples in there. Even if they don't control chart them, they put them in so that they can detect if the calibration has drifted or the instrument has drifted. So control charts operate on a pull philosophy. So this is what happens, say, when you have, let's use something that, I don't know how fastidious you guys are in terms of maintaining your vehicles, right? But like if, do you guys make sure your wiper fluid is done well? You know, my car, you know, that's not critical, but it's important, right? And so when the wiper fluid low light dings, I go and I get wiper fluid and I fill it up, okay? Do I check it? What was the word you just used? Fastidious? Can I get a definition of that? Yeah, like particular, like you're like really meticulous and you're going to make sure it's tight. Your car, all the lights are off, right? So no matter what light it is, as soon as it comes on, you go get it checked, right? And yeah, so fastidious, that's a good word. And so so I'm not that fastidious, but I like to have clean windshields. And so whenever that light comes on, I go, but do you see how that's a pull philosophy? I don't check my wiper fluid level ever. I wait until it tells me it needs attention. So it pulls my action. A calendar version would be every Monday I open the hood and I go in and I look and I stick a little dipstick in there and I say, okay, I still got fluid. I can go drive. You know, that would be a calendar-based action, and I don't do that. And almost nobody does that for their wiper fluid. Okay. And we'll get to the check engine light later. Okay. So that's a different beast. Okay. So we will calibrate only when our system tells us it's needed. So you see the pull of the action. So you're going to be rocking along with your control chart, and you're not going to go do any research necessarily unless you're curious. But when it goes out of control, then you're going to go look on the internet, or if you're doing the Fitbit, you're going to analyze what you were doing yesterday and why you didn't walk as much or why you walked a lot. You know, you can go out of control on the high or the low side. And so this could save money by focusing on the problem, not the schedule. But it could also indicate when you maybe need to spend money. Maybe your instrument is so drifty and your process is so out of control that it's constantly impossible to keep a good calibration going for more than 4 hours or something like that. So it improves quality because the performance is frequently monitored, but I would say monitored appropriately. You know, you're not wasting a lot of time recalibrating, but you are monitoring. Now you can wear yourself out with this, and you can put a control chart on every piece of equipment in the lab, and then you're wasting time now. You need it on that key indicator. So that's part of knowing your operation is what thing in this operation indicates if the whole lab is in control. So it might be one of those major output type. Maybe it's a particular GCMS, which would capture the operation of the instrument, all of your standards, all of your balances, and everything. So you would need a key process indicator so that you can be as efficient as possible. Okay, here's the standard that Jay found. It's an ASTM standard. It's the standard practice for use of control charts in statistical process control. So, here it says the control charts are used to continually monitor product or process characteristics to determine whether a process is in a state of control or not. So I'm kind of going through this and showing you, some of the terms and definitions. So these are some important pieces. Now, this applies to variable data that is continuous numerical scale. So remember I talked about you can't really use gas prices or difference in gas prices because it really doesn't show up to be continuous because it's rounded to the penny or to the tenth of a penny, and it doesn't change very often. And so we're really focused on continuous numerical data. And I talked about special cause in the ASTM. They're calling that an assignable cause, right? And they're contrasting that with an unassignable cause. Like the random fluctuations, it went up a tiny bit. What was the assignable cause to that? Well, you don't know because it's just lots and lots of little fluctuations occur on an everyday basis. Let's say you're tracking your steps, and one day it was 6,100, and the other day it was 6,050. What happened? Well, you have no idea. It was 50 fewer steps. That's not assignable. Okay, a special cause is. Let's say you had to park, way out of Bowers, and you get here and you forgot your backpacks, and then you got to go back. Well, that's an assignable cause. Okay, you didn't have your coffee and you weren't thinking. Okay, then there's chance causes or common causes. So I in the notes I talk about common cause. Well, here's also another name for that, chance cause, and they may be undefinable. Okay, and then this even has a discussion of the control chart. It's the statistical measure, based on a statistical distribution of that measure to indicate how common or chance cause variation is inherent in the process. So we want to learn about our process. And then we have these lower control limits, and then later you'll see an upper control limit definition. So this right here is what we're going to be setting as our minus 2 sigma. So we'll have our mean, and 2 sigmas below that would be our lower control limit. Now this is an interesting standard. They have lots of different kinds of control charts, a moving range chart, an R chart, and so on. We're not going to get into all of that, but you have the standard. If in the future, if you read through the standard and in the future you say, oh, I need to actually use this kind of control chart, there's several examples in this standard. It's pretty long, and you can see how different charts will apply to different kinds of processes. Okay, we have our control limits. They're used as a criteria for signaling when action is needed. And so it talks about an example of a 3 sigma limit. We're going to use a 2 sigma limit. And then this is just the general topic that we're discussing today, the statistical process control. So it's techniques for improving quality of a process output by reducing variability using control charts and corrective action strategies. So we're not actually taking corrective action. In fact, I really don't want you to do that. There'd only be a few examples in this class of where you might be able to take corrective action, and that would be people that are monitoring their steps or monitoring some personal characteristic where you can actually have somewhat of control. So like if you're monitoring your steps, just go about your day as if you're not. Okay, don't say, well, yesterday was low, so today I'm going to make it high. You're introducing variability that you don't need to do. Just when it goes out of control, just investigate what happened that day to make it go out of control. I don't think there's other processes that you guys can affect, like the exchange rate for this currency or some stock price. Like it gets low and you're actually rich and go buy a bunch of it and drive the price up. That'd be nice, but anyway. And then there's the upper control limit, which we're going to use as 2 sigma above the mean. Okay. Now, the significance. Let's talk about the significance of the statistical process control. And so this is the main part. This principles of statistical process control. It's trying to convert inputs into outputs. So if we're reducing the variability and trying to control the inputs to our actual process, we will control the outputs. And what are the outputs in a forensics lab? The output is evidence compared to various limits. Okay. We really can't control that, but we can control our process. We can control our calibrations, we can control our instruments, we can control our procedures. So those inputs are the things that we're trying to control. And then whatever comes in the door and we analyze and goes out the door is not in our control. We can't control the concentrations of drugs coming in or the quality, the accuracy of our results, but we can control our process against known standards. And so there are some standards. There was one of those definitions in here too. What was it? Yeah, this accepted reference value, ARV. So this 3.1.3 is also important. Okay, so this is our standards. And in an analytical chemistry lab, which is what you're going to be running or in, let's not get ahead of ourselves. You'll be in the lab first, then you'll run the lab, right? So you'll be there, and we're going to practice against those standards because we have no control over what's seized out in the real world, but we have control of our standards. And so luckily, NIST and these kinds of governing bodies will provide standard reference materials. And so you'll have, like we have up on the second floor, they've got a safe. Go open it up, and inside there are our drug samples. And you analyze the real thing and show that you've got a good process. Okay. Now, these are the two stages that we're talking about. So I've been calling it a training stage. So in the first 15 days of data collection, you're in the training mode. What you're doing is you're training your understanding of how the process is going to proceed. This is stage A in this ASTM standard, process evaluation. So you're gathering data, you're making up your own historical data for those first 15 days so that you can calculate the standard deviation and understand your process, right? It's easy to calculate the mean. You collect 3 or 4 of those data points and calculate the average. That's your mean. But what's the standard deviation? You know, it takes a little longer to understand that better. And so we'll let the process fluctuate for 15 days so we have a population, and then we'll calculate the sigmas. So that's stage A. That's the process evaluation. And then stage B is the process improvement. Okay. So we're going to follow that, and we're going to look for special causes. And so that's the rest of the semester. So from, day 16 on, we'll see if it's in control. And then midway through, we'll have a midterm quality report. I think it's right before spring break, where you write it all up. And this year, I'm going to do something different. There's a rubric on there that teaches you how to give good peer review. A lot of science is based on peer-reviewed research. What is peer review? Have you guys ever really done that? There was in my class, a PChem lab where you get some comments back from the TA, and then you have to respond to those. Now you guys are going to be in charge of giving those comments. So everybody in here will evaluate, peer review 2 other reports. So you'll submit your reports, and you'll get 2 more. You'll go through, and we'll use there's different ways. Some people call it the evaluation sandwich. You give something positive, some critical input, and then end with something positive. That sounds really touchy-feely, but it's actually psychologically valid, right? It's so hard to receive critical input if that's all you get. But if someone notices something positive first and then says, yeah, but this could be improved, you're more receptive to the improvement part. After you've already said, okay, well, is there anything good? Yeah. I'm going to start out with saying this chart was well formatted, or this paragraph was well written, okay? And it needs to be specific. It can't just be vague, like Good job. Now let me tell you how bad it was. Right? So you're going to learn how to give good feedback. That sandwich method is one way. The other way I've heard, which is a little bit more memorable, is roses, thorns, and buds. Right? So picture a rose plant. The flower, nice and pretty flower. That's what you see from a distance, okay? But every rose bush has the thorns, right? Those are the things that could be improved. And then the bud is something that's not there yet, but you're looking forward to it. And so I always start with that rose, then talk about the thorns, and then finish up with the bud. What are you looking forward to when they make these changes? This report will be much better in this specific way. And again, it's got to be specific. So I will actually grade your evaluations. So you're going to have the report and you're going to have the evaluations, and I'm going to go through and see if your evaluations followed that scheme and if your evaluations were specific, not vague, okay? And then the second time you turn it in, the final report, I'm going to look to see if you took the peer review into consideration. Okay, so you will take the input from your two reviewers, you'll make a table. Reviewer 1 said this, 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 and this. Here's how I made the changes. Reviewer 2 said this, this, and this. I made those changes, and here's my report. And so I'll be looking to see that you made those changes and responded to the peer review. That's how science is done in the modern day, okay? Whether it be a research paper or if you're preparing a document from your lab for evaluation from another lab, they're going to go through, they're going to find positives, they're going to find things that need to be changed, and then they're going to, finish it up. So you guys will be trained in how to do that after the semester. Now let's look at some of the rules for determining if a process is in control or not. This apparently is named after one of the first companies that did this kind of work, Western Electric. Okay, and so a shift in the process level is indicated, and look at all of these rules. One value follows outside of either control limit. So that's the one we're going to use. Okay. So we're going to use rule number 1, but there's lots of others. We have action limits, which are 2 sigma away from the mean. We also have warning limits, which are just 1 sigma away. That contains 68% of the variability. So about 20% higher, 20% low of that watch limit might be something that we would look for. And so this is saying if it's 2 or 3 times outside that watch limit or warning limit, then the process is out of control. We're not using that one, but it could be one that we use. 4 or 5 consecutive values outside of plus or minus 1 sigma. Again, these are things that shouldn't happen in a random process. So you shouldn't have 4 points outside of 1 sigma. Okay. How would you calculate the probability of that? Well, if they were like right outside that 1 sigma, there'd be a 20% chance of that being the case. What if there's 4? Well, it's 20% of 20% of 20% of 20%. So 0.2 to the 4th power. Not very likely. Okay, so that's what they're saying. This isn't in control if that's happening. 8 consecutive values on either side of the center line. So if you're above the mean 8 times, it's 0.5 to the 8th power. Not in control. That shouldn't happen. You shouldn't have 8 points on one side or the other because, randomly it should be on either side. It's a 50-50 chance of being high or low. You might have 3 or 4, but 8, that's probably not random. Okay. Okay, so 6 consecutive points in a row that are increasing or decreasing. So you're starting to see a trend. So they're not outside the limits, but they're moving up. Okay. Again, that's even less than 6 just on above the mean, but 6 always above each other. Then you're seeing a trend. 15 points within 1 sigma. That's a little strange. So again, 15 points within the range of 68%. There's 68% chance of 1 data point being in that range. 15 consecutive ones, that means your sigma has changed. So now you have a new sigma. So this is detecting whether your process has tightened up or loosened. Okay. Alternating up and down. There's some processes that cause your data to go up and down, up and down. And so this, again, 14 consecutive points going up or down, or 8 consecutive values, outside of plus or minus 1 sigma. So these, you see all of these different rules, but this is the key right here. It says these rules should be used judiciously because they will increase the risk of a false alarm, okay, in which the control chart indicates a lack of statistical control when it's not. If you cast a net that catches all of these, you're constantly going to be trying to fix a system that's not broken. So you need to figure out which one of these is the key indicator for your process. So we're just going to use that top one. One value falls outside of the control limit. So in Minitab, we could do these control charts. We go up to menu, stat, control charts, variables for individuals, and individual charts. Here we pick this volume data, select a stamp, the date stamp, and we pick the mean and the standard deviation that we get from the historical data. And then we have our multiples of the standard deviation, and then we have all of these options. So these variables, these tests right here are from that ASTM standard. So it's built into Minitab. 1 point greater than K standard deviations from the center line. So in this case, we have it greater than 1 standard deviation. We could put a 2 there, and that'd be what we're doing. K points on a row on the same side of the center line. So this is saying 9 points above or 9 points below the mean. It needs to ring the bell and tell us that our process is out of control. So we could put all of these tests and activate them, and we would constantly be running around chasing our tail, trying to fix a process that's not broken. Okay, here's zoomed in on all of this. Okay, and so here's an example of a control chart in Minitab, and we see that it's flagging this data point, even though it's not outside the control limit, and it's got a little 7 by that. And here it's got, these are flagged with 1s. And so these warnings are explained in the session log. The nice thing about Minitab there's lots of nice things over Excel, but one of the nice things is it has a session log, which would really do a lot to satisfy your accreditation standards for a crime lab, because everything you do to the data is logged. Is that the case for Excel? No, there's no log in Excel. You could go in and you could take a formula and you could change it. If you have a cell of like 4,000 formulas, you could go in down there and cell 1,500, and you could change that formula to make it do a certain thing. And it would be really hard to detect that because Excel doesn't have any quality control in it. It doesn't have any session log. If you were to fiddle with the data in a Minitab, there'd be a record of it in that session log. So if you're using Minitab to control chart your data, you get this session log, and you can see test number 1 point failed, was more than 1 standard deviation of the center line, and it failed at points 17 and 18. Or test number 7, 15 points within 1 standard deviation of the center line. This failed at points 15 and 16. So, these are the different warnings that you see in the session log, and this session log keeps track of everything that you do in the program. So let's look at some of the control charts that you're going to have. You have the 15-day training period. Notice during that 15-day training period, what we'll see in the spreadsheet is just the data. We won't see a chart. After you get that data, you can calculate the standard deviation and the mean, and what you have is the mean, and this is watch plus S. It should be sigma, but it's kind of a pain to do Greek characters in the legend. In fact, I'm not exactly sure how to do that in the legend. Okay, so we'll stick with S, even though it's kind of wrong. We have a population, so it should be sigma. If you can figure that out, man, that's great. So. And then the action limit is the mean plus 2 sigma. The lower watch limit is the mean minus sigma, and then the bottom one is the mean minus 2 sigma. And then we have some indications here of 4 data points that were out of control low. Now, it's nice if I have a different color. It's not required, but it'd be nice. Nice touch. If the training period's a different color. So how do I do that? Well, I plot all of the data on my chart, and then I grab the training data and I plot it on my chart next. And since it's plotted next, it shows up on top of the other data. And I just make it a different color. So that's how I show the training data a different color than the whole data. So there's actually two data points here. One's black and one's green, but the black one's behind the green one, so you can't see it. Okay. And that's how you get the whole thing to chart out just nicely. Also down here at the bottom, if I were to include every date, they would overlap on each other, and it would be really confusing. So this is not a XY scatter chart like the ones you used in CHEM. Okay, we were always doing XY scatter. This is a line chart. And these are called categories. Okay. And you can format those categories as dates. So you go into Excel, you click on the x-axis and you format that x-axis, and the labels, you go in and you say, they're dates. And you can set the date format, and you can rotate that text vertically, and you can skip, like if you have 7 days of data, you can skip 7 categories and it shows up every Monday. And so these are Mondays. So I have every Monday date shown, and I would like for you to do that to keep the x-axis simple. Okay, I might tick off a point here for this collision between the label and the date. I would need to scoot that x-axis up a little bit so that they don't overlap. So I want your chart to be formatted as exactly like this, if possible, okay? Because that's part of the course, is learning how to control all of these different formatting features. So over here I'll put skip 5 or 7 categories to show Mondays. Does that make sense? It's to skip 5 or 7 categories to show Mondays. If you don't have weekends in your table, then it's every 5th one. It's Monday, skip Tuesday through all the way through Friday, and then Monday again. And so it's just showing the Monday dates. Yes.
If it's always like tracking our data on like a Tuesday or a Thursday, should we set it to go ahead and skip to the Thursday or Tuesday? Or?
Yeah, I'm not really that concerned about it. Yeah, so as long as it just shows once a week, that would be fine. So you could have Tuesdays, so that'd be fine. Yeah. Because I'm not going to get in the calendar and say, is that a Monday? Yeah, but I do want it to be clean like this, where all the dates aren't slammed on top of each other. And you'll see what I'm talking about. When you format that as the dates, they'll be all over each other. And then you figure out how to skip those, and it'll clean up real nice. And then you can do a grid line on the main ones, and the other ones are the minor tick marks. And so we just have a main increment grid line. Okay, so this is how we set up our data tables. So we have the data here. So in this case, we just have straight data. We're not taking the daily differences, but it doesn't matter either way. So notice up here we have some cells that we're going to anchor later. So the measured mean for our data is just the training period. That's really important. Okay, it's just the training period. It's not going to be all the way to the bottom of the table. It's just those first 15 days. So do you see how that ends right here? Okay. And the standard deviation ends right here. So that's our historical data, and we're going to see if it stays with the same mean and the same standard deviation the rest of the semester. Okay. So that's what we're calling a training period. We're kind of training our system to look at this process. This training period idea also is how AI works. There's a training set, and then there's the output set. And so this is our training set for for our process control. Okay, then we set up these other columns. There may be easier ways to do this. No, this is the easiest way. There may be cleaner ways to do this, because this is just, I don't know, it's visually it's irritating to me, but I don't know what other way to do it. We have the mean, which is just this cell anchored right here, and it's copied down. So I have the same number all the way down in the table. And that produces that horizontal line called the mean. So at every date, I have the same number for the mean. And then I have the mean plus, you know, if you were fancy, you would come in here and you would say mu plus sigma, right? Now, it's pretty easy to do, you know, symbol font or Greek characters in a cell. And so this one would be mu minus sigma, okay? And the action limit would be mu plus 2 sigma. And this action limit, the lower specification or action limit, would be mu minus 2 sigma, okay? But it's, you know, isn't that kind of, I don't know, you look at this table and you're like, wow, the same number all the way down, you know? But I don't know. Like I said, there may be a cleaner way to do it, but this is the simplest way to do it. You make sure you anchor those cells, right? That standard deviation is anchored, that the average is anchored. You double click the corner, it goes all the way to the bottom. Okay. And then I can plot the date and the data and include all of these other columns. Now, every data point beyond the action limit must trigger an action. So that minimum action is to make a log entry, okay? So let's do something fun. Let's learn some new skills. Here's one way to do it, right? If in this alert column here, I can use this if-then statement. And I can use the OR function. So this is a Boolean function. So this piece right here, this piece will return true if D8, which is our data, is greater than H8, which is our upper action limit, or, comma, D8, our data, is less than our lower action limit. So you see the or? If I'm above or below, then I get true for that function. If the first part is true, then after the first comma, I do this. If it's false, I do this. So we're saying if this, then, that first comma is the then, this, else, the second column is else, this. Okay. So what is this last this? It's two quote marks with nothing in between. So that's essentially filling the cell with nothing. So that's a handy thing. If it's above the upper limit or below the lower limit, I'm going to say beyond action level. Otherwise, I'm not going to say anything. That's what that function is. So this is a good way to do it, but this is better, okay? This is a nested if-then statement. So I'm going to test the upper limit first. So I'm going to type in, and then these are Excel formulas, and so I'm going to come over here, once I find my little pen, and I'm going to say it's equal. So equals if, open parenthesis, if D8 is greater than H8, I'm testing it against the upper limit. Then, so here's the first comma, then say, in quotes, above action level. Else, so that's the second comma, else, do another if. So it's not above the action limit, so let's test the lower one. Else, if D8 is less than the lower action limit, then type in below action level. Else, do nothing. So I test if it's above. If it is, write something. If it's not, I test if it's below. If it is, write something. If not, then the third category is nothing. It's inside the limits. So that's even better. And that way you can look at the table and see it was above or below the action limit. So I don't know what the maximum is. I don't think I've ever hit it. But, you know, this nested if-then statements, this is how you can test for lots of things. And you can just keep nesting them. If this, then this. Else, if this, then this. Else, if this, then this. And you can just keep going ifs until, you know, you can have 7 or 8 criteria there. That's crazy for us. We don't need that. We can just do 2 criteria. If it's above, right above. If low, below, right below, or do nothing. Okay. So this alert log is why you need something researchable, right? You need to know when it's above the limit, you need to be able to go investigate. Like if it's a stock price, then you go look at the news and see what happened to that company. If it's your Fitbit, just think about it, right? Had somebody tracking, it was a weight thing. They were tracking their daily change in weight, and they got the flu. And you could detect, like from their weight gain, you could detect that they got the flu. It went down, and it was below the lower action limit. And they were like, yeah, I was sick for 2 days and didn't eat anything, drank water. So, yeah, so that was interesting. Not a recommended weight loss program, right? So you come down here. This is a comment. This was tracking weather or temperature changes below the action level. A cold front came in. And so this is maintenance being performed on the building. I don't know. That's kind of interesting. Okay. Higher than usual building use on this day. So this must have been inside. So they were checking the temperature changes in the building. So that's pretty cool. If you're doing a stock price or something like that, go ahead and put the URL for your research. So even if you're doing the weather, go ahead and put a link to the page that said that what happened to cold front or something like that. I want to see that you actually did your research. I'll click on those links just to make sure. All right, so your control chart should be formatted just like this, except for this little date collision down here. Okay, so fix that. And then notice I put in a little checkbox to not have a bounding box. Excel by default puts a box around the outside edge, okay, which is distracting, okay? So this is the outside box that I'm talking about. So I'm going to put here, no, okay? Because it's unnecessary, and there's no reason to have it on your chart. People get freaked out, though. They're like, oh, he says delete the box. And so they delete this one. And like, no, that's not what I'm talking about. I'm talking about the extra box around the outside of the chart. So click that in Excel and say no border on your chart. And that will get rid of the outside one. But this one is good. So yes on this one. Okay, because that's telling you where the data area is. It's this outside box that is useless, and Excel just does it by default. And so when you paste it into Word, you have this extra box around your chart. And in the ACS guide, it says you don't need that box. And so I'm going to try to stick to the ACS format. Okay, we talked about this. Can you remember what we called this data? What's wrong with this control chart? This says flow rate, but I think this was gasoline data. I just changed the axis. So I'm going to let you stew on this one. What is it? What's wrong with this control chart? It's going a whole lot above the action limit, and that's a clue. It looks like it's shifted up, but and you can see the training period was used to set those limits. Okay, and so here's notice the training limit was here, and so it set those limits, and now we've got this limit up here, and it's going out a whole bunch of times. So that is an indicator that something's wrong, but it may not be an indicator that something's wrong with the process. So look at this data and tell me if something's wrong with the data. And it's not exactly because it's always out of the red zone. Okay. What's that? It's the data as a whole is bad, but why? There's a pattern. Tell me what the pattern. What is the pattern you see? What's the stays the same part? There's a lot of sameness in this data, isn't there? No, that's not it. Yeah. In fact, there are no halves even. It's not continuous. It's not continuous. Notice it's digitally rounded. So we have either 0 or 1 or -1 or -2. That's not continuous data, okay? There's only 4 answers. And so we can't have that in our data. So that's why I was such a stickler on data choices, because what we're doing is we're taking this data that's not continuous and we're using standard deviation and mean, the Gaussian statistics, and Gaussian statistics are based upon standard continuously variable data. And this data, so what will happen is when you apply Gaussian statistics to this data, you get this, what you noticed over there. What was your name in the red? What was your Tyler? Yeah, what Tyler noticed was that, hey, we're out of control a whole lot. And it's because we're applying continuous statistics to non-continuous data. Yeah. And so we're going to be chasing our tail trying to figure out why it's out of control when it's not out of control. We're trying to apply continuous statistics to something that's not continuous. This is what we get with digitally rounded data. And so we don't want to use something that doesn't have the significant figures that we need. We need to have variability in the smaller place values, right? This is the first place value, what we call the most significant digit, the MSD. So the ones place is the most significant digit. Okay. And it would be nice if that most significant digit didn't change, but lots of these least significant digits change. So this is the MSD, and this is the LSD, least significant digit. So a really good process that's in tight control, the most significant digit doesn't change. You've got a couple of digits, and then the least significant digit is the one that's going up and down, or maybe the last 2 is going up and down. So you have a couple of certain digits and a bunch of uncertain digits that change a lot, okay? You can still have sort of continuously variable data if your most significant digit changes, but it's got to change by a lot. And so think of step count, 2,000, 10,000, 8,000, whatever. It's changing a lot, but you have lots of numbers in between, right? Because it's counting even the, down to the ones place. And so that one will work, but it's crazy variability, right? From 2,000 to 10,000, that's a lot of variability. But if you look at, I've seen students do step count, and they'll get a mean and standard deviation, and it'll be somewhat in control, and you'll detect those days that they're out of control. Like a waitress person was, they had the double shift, so their steps were crazy out of control because they're just back and forth for 2 shifts to the kitchen, and so they were easy to say, yeah, my feet are killing me because I did 18,000 steps because I had the double shift. What's wrong with this one? Yeah, trend. Boom. So that's not in control because it's not staying the same. A controlled process stays the same. So this is what we would see with temperature. And so one way to do that is to take the derivative. When you're taking the daily difference, you're taking the derivative. And so you're just taking that slope out of it, and you're looking at changes in the slope. Okay, we can automate control charting too. It is kind of tedious to collect your data, go put it in the spreadsheet, update your chart and all that stuff. And so these circular control charts are really popular. So this is a circular chart recorder that, let's say you're trying to monitor the relative humidity in the lab because you have samples that are hygroscopic and they'll soak up a lot of water, or whatever. And you can buy these monthly discs. And so this thing collects a month's worth of data on one disc. Isn't that cool? Yeah, and so it's measured. You can read the current value up here, but you can follow along. And so there's, down here it's hard to see, but you have like February and March and April or whatever, and you can follow along and you can see the days. I mean, that thing turns slowly. If it takes a month for it to go all the way around, but you could see, oh wow, last month or 6 days ago it went out of control. And so then you can make your corrective action. They're not that cheap, $960 on Granger. But, you could compare that to the amount of time it would take a person in the lab to log this data and do the Excel or Minitab or whatever. And so it'll pay for itself pretty quickly. You can also computerize it. So this would be paper-based. You scan it in, I guess, if you wanted a record of it. Or you can buy these that, they just digitize the whole thing. And so this is nice. I don't remember what the price was on this one. So it's they make electronic control charts. And so what y'all are doing by hand can be automated for sure. What questions did y'all have? Let's bring up, the check engine light. Let me go talk about the check engine light real quick when we'll be finished. Okay. My problem with the check engine light is I think they have this situation, right? Everything is built into that check engine light, and it comes on for critical stuff and for non-critical stuff. And so after a while, you just ignore it. And so a process that's constantly going out of control, you just normalize that variability. And you say, well, I drove to work, I drove home, the check engine light was on, it must not have been too serious, right? And so you're taking the noise and you're just ignoring it. You're folding it into the process. That's terrible, okay? It can be terrible, okay? I drive with my check engine light on. Every time it gets moist outside, bing, comes on. And I'm like, if you wanted me to do something about it, you should have put some text. Tell me what it is, right? But it's just boop, the light, And I even saw the little song, like the little Christian song, "This Little Light of Mine," the little check engine light. So they've ruined their own process control by setting up too many tests that have the same signal. Okay, now. This is what leads to things like the space shuttle falling out of the sky, Space Shuttle Columbia. Whenever that shuttle was destroyed on its return to Earth, I was working at Pantex. And again, Pantex is a place where they maintain and refurbish and decommission our nation's nuclear stockpile. So it's a serious place to work. And the company that was our parent company also made nuclear submarines. Also a very serious place to work. And so one of the main guys in the parent company got put on the commission to study what happened. Why did this space shuttle get destroyed and why did we lose these lives? Okay. And as they're building the space shuttle, they have specifications. And you have a part that's produced and it doesn't quite meet the specification. And so you have to analyze whether it's still okay to use it, or do you reject that part and rebuild it, okay? They had the specification levels tightened down so much, kind of like all these tests. The controls were so tight on all of those that they lost their significance. And they started writing variances on all these out-of-spec parts because it was the check engine light problem. The check engine light was on all the time on all these individual parts. And so this investigator asked the NASA, how many parts on the space shuttle did you have sort of overrides on the specifications? Because he worked with nuclear submarines and they have like single digits, like 2 parts or 3 parts on the whole sub that are out of spec. They had over 1,500 on the space shuttle. There were 1,500 processes that were out of control, and they got used to them being out of control, and they had successful launches with them out of control. And so they said, well, it must not be a problem. We must have just tightened down our specs so much that it's a check engine light and we can just ignore it and still be successful. So that's the problem with tightening down your levels. Your levels need to be appropriate, not just tight. So you don't tighten everything down so tight that you have to ignore it because it's giving you false flags. Only set those levels at the important processes so that when it really is out of control, you know you can't operate. And when it is in control, you know you can operate. So that's, don't get overzealous and say, I'm going to try to control everything. Find the key process indicator and control that one. And then you'll know over time that you have reliable results. So, good. See you later.